All right, try not to swear on camera challenge 2024. Let's go. So I'm Nick, this is Justin. I'm immediately going to start off by throwing my co-presenter under the bus terribly. If you took 1d6 psychic damage from the title of this talk, this was all him.
Bad jokes don't stop.
No, they get worse. The puns get worse, I'm sorry. So what are we doing here? We're going to talk about how to determine, so radios lie. All right, the moral of this talk is that your hardware is always lying to you. And in this talk, we're going to show you how hardware or your radio lies to you, what you can do about it, and if your hardware is not lying to you, what is that real station that you're looking at? What is that transmission? How do we find it? What can we do about it? I see C and Laura is in the audience here. If you guys, raise your hand if you attended his talk this morning. Okay, this is sort of the mathematical inverse of his talk. Whereas he was talking about deliberately producing interference or transmissions with devices that aren't supposed to be producing interference, we're going to talk about how everything in the world that has an oscillator in it is producing noise, and all of that is leaking into your stuff, and how to mitigate that. So how not to do what you're doing on purpose. So I covered the agenda pretty much here because I'm getting ahead of myself, but what am I looking at? Is it real or is it fake? How do I find it if it's real, if it's noise that I don't want to be in my radio? And what can I do about that noise? How can I get rid of it? So we'll skip straight over that one. What are the tools that we use? There's a whole broad array of tools that we can use to find more information about the signals that we're receiving. Some of those tools we'll talk about later in the talk, but there's a lot more information in the stuff that you're receiving deliberately or incidentally than you usually would assume. There's a lot of clues that you can take from the stuff that you're seeing in the spectrum, and we'll talk about what those clues are and how you can use them to figure out what you're actually looking at. How do we determine what a signal actually is? Is it a real signal that we're looking at, which is being transmitted deliberately from somebody else, or is it interference from a bad power supply? Is it a birdie, a signal that's created entirely within my own radio that doesn't exist at all? How do we figure out what clues is the signal telling us that let us figure out what that is? And how do our tools lie to us? How do our radios lie to us? How do spectrograms lie to us? And how can we work around those deficiencies to try to understand what the radio, what the hardware is actually telling us about our RF environment? So tools of the trade. Justin, you can speak more to this if you want, since most of this is his hardware.
Cool. I'm gonna take this off because I have a really hard time standing still. Make it hard on the cameraman. So what tools do we have and how do we use them? That's sort of where we're going to go next. There are unquestionably much better, more professional tools than what you see on the screen. But I wanted to talk about what a lot of us have or have access to. So on the left-hand side, we've got some radios. RX-88 is a HF, really 0 to 148 megahertz SDR that'll let you see 64 megahertz of spectrum at a time. And it costs under $200, which is pretty darn cool. The Web 888 is sort of a web version of that you can access over your web browser. So if you used like a Kiwi SDR or Web SDR, you can have one of those yourself with a Web 888. And then various, RTL SDR dongles and AirSpy. On the right are some filters. So we'll talk about some of the problems that these SDRs tend to have and how do we get over them. So there's some different filters you can use. Filtering is really the solution to a lot of those problems. So we turn our SDR on and we stick the little antenna that comes with it, in it, and we start looking at something. Is the frequency or is the signals that we're seeing there, are they real? Are they something the radio is creating? Are they actually being used? And so one key point to make is that nobody makes money or has good communication using an unmodulated carrier, right? So if you just see a tone somewhere, it might be real, but there's a good chance that it's not. And when we say real in this case, there's sort of two pieces of that. There's is it really real? Is it actually being something that's broadcast, or is it just an artifact of my radio? And then there's is it useful? Is it noise? Is it an unintentional radiation? Or is it some signal that somebody's trying to use? So we'll go through sort of some of the pieces of the questions we can ask ultimately to decide whether something's real or not. And a piece of that is it a fixed frequency versus a changing frequency? Right? So this is a chunk of the spectrum. At the left-hand side there, we have like 26 megahertz, and this goes all the way up to like 28 megahertz. So this is our CB radio band in HF. Up here is our ham radio 10-meter band, some various stuff in between. And so there's some things we can see from this picture that like we can start answering those questions in, right? So there's a whole bunch of fixed frequency signals there, right? We've got some wider signals, we've got some narrower signals, we've got some really wide CB signals. We've got some amateur radio signals over here that are, CW, FT8, voice, lots of different signals there. But the key to the signals on that page that are real, and by real meaning intentional, is most of them, show up a line on my spectrogram. So this is time, this is the past, and this is the present. And so we're seeing a picture of the past to the present here on the spectrogram. And so everything that makes a straight line up and down, there's a chance that that's real. Stuff that doesn't do that, those may not be intentional. And so if there's a lot of questions about these funny things. Where did those come from? What are they? Spoiler, they're arc welders all over the world that they use for welding plastic. And they show up at different times of the day. They're using the 27 megahertz ISM band, which is like kind of here-ish. But, they show up other places, including over here and over there. And yeah, basically 13 to 30 because there's lots of unintentional radiators in the world. And so that's the kind of questions you can ask, right? So these aren't being used to send data. These are being used to weld plastic. And then, so intentionality versus noise, right? Signals, as we saw on the last page, you saw a lot of straight shots through time where signals are staying on the same frequency. We can also look at, wider modulation and intentionality, right? Does that look human-made? Does that look random, right? A lot of times, these human-made signals will look very clearly, geometric. And that can help us to understand whether something's real. And geometric can mean, these nice rectangles on the spectrogram, or it can mean these funny, sink-shaped Gaussian-like things. Those are all intentional signals. So if there's a well-defined spectral mask, it fits within a clear spectrum, and it kind of looks geometric, those are hints that it might be real. The other thing is that generally intentional radiators will occupy a fixed part of the spectrum. They're not going to use a huge amount of kind of random spectrum because they're licensed, and their license only lets them use a certain amount of spectrum. So if you see things all over the place, that may be a hint that it's not real. And then, is there stuff in this band licensed to transmit, right? So like on the last slide, we talked about the ISM, the Industrial, Scientific, and Medical band. Those bands are unlicensed bands that people can use all over the world for different things. And so there's a whole lot of uses in those bands, but then there's also some uses that are maybe not intended to communicate. So that's the kind of stuff to look for. So another question we can ask is, okay, it looks kind of stationary in frequency over time, but does it drift? Does it change? And how does it change, right? So these are some different signals that change in different ways, and we can talk about what they are, and actually we can talk about that we don't know what they all are. So these are just some spectrograms that I took at my house. And, we've got some like sort of funny wobbly things over time. Each of these is maybe 10 seconds or 15 seconds of spectrum. And, this guy, probably this thing over here, those are all very likely switching power supplies. So you have a switching power supply, it's got an oscillator in it, it's cheap, it changes temperature with load, changes temperature over time, and that oscillator drifts a little bit because nobody cares to keep it very stable because it's cheap, right? And so as that happens, those switches, the harmonics of those switches show up all over your frequency spectrum, and you see these little warbly things. And if you're listening to them, they kind of warble as they go along. Those are probably not real. Somebody's not using this to communicate. That's a byproduct. Another thing you'll see is, and we'll talk more about this as we continue to go, but frequency things like this. These are a little harder to see probably from a distance, but these have a little funny shape at the front end that looks actually kind of like this. This is a different plot, but these do the same thing. And they, over time, they both drift a little bit, and they change bandwidth. They widen and come together and go apart. This is my furnace. It's definitely not being used to communicate. But that's what happens when my furnace comes on. It's got an old, brush motor in there, and when the brushes pass the commutator, you get a spark, and it occupies my entire HF bandwidth. So it's not a intentional radiator, but it's definitely a radiator. And then Nick and I were arguing earlier about what these might be. You see a lot of things like this, and that happens as different devices turn on and off. So Nick's idea was maybe it's a float charger for a battery, where you've got a charger coming on for a second, putting a little current into a battery, and then realizing, oh, now the battery's topped off already, I'm going to turn back off. So this is about 5 seconds, and then it goes off, and then about 5 seconds later it comes back on. It's periodic, but it's not fixed frequency, and there's a whole bunch of them across the spectrum, which usually means that there's a bunch of harmonics, so it's something that's switching hard on and off. Those are all hints. Another one is patterns of life, right? So we see stuff on our spectrum that changes, right? What's going on? And a big one is the time of the day, right? We all tend to keep a schedule, some of us later than others, and things happen with a rhythm. Do you see things that come and go at certain times of day? Does something show up only when your neighbor's there, right? Does something show up just in the morning or just in the evening? And so these are a couple of examples that show up in my house. This one I have to deal with, but I left it here because I wanted to get a good spectrum of it for this talk. This is a bad ballast on our fluorescent light. So this is light on, light off, light stays off, right? And I think Nick commented that this is not a bad ballast, this is an area denial weapon. This is keeping my house safe from drones, so that's why I haven't removed it yet, but now I need to fix this. But it's very obvious, and the first time it came on, I didn't know what it was, and I had to go hunt it down and figure out, hey, where is this thing, where did it come from, what is this? And we'll talk a little bit as we go on about kind of how you can do that, but flipping on and off switches is a real good way to try to figure out, is it close to me or not? There's other things that we can think about, right? Is a school in session? Is there a football game going on, right? Big potential arc lamps, right? Wireless microphones. We were at the party last night trying to figure out what an emitter was, and I think it ultimately was the wireless microphone. But that kind of thing, or questions you can ask yourself to try to figure out what is this thing I'm seeing on my spectrum. Your radio lies to you a lot. I think Nick's going to take over here and talk a little bit about how really there's a lot of pieces to different radios, but modern SDRs especially are really good at lying to you.
Yeah, so Nyquist comes with some advantages and disadvantages. A sampling radio is uniquely vulnerable to some effects that you wouldn't otherwise see in an analog radio that aren't immediately obvious. Sometimes it'll do some bizarre things. Raise your hand if you have a RTL SDR or have played with an RTL SDR. Keep your hand raised if it's ever absolutely confused you with bizarre stuff that you've received that you don't understand why it's receiving it. Yeah. It's a lot easier with an AM radio or a handheld radio or something which is completely analog. Usually the signals that you're receiving make sense. Sometimes not. One of the curses of the RTL SDR is actually one of its strengths, which is it's in addition to being extremely cheap, it has a completely wide open front end. And by that I mean that its ADC, the thing that's doing the sampling and capturing the RF, has basically nothing except an amplifier in between it and whatever horrible crud you're putting into it. So it has, as a result, good sensitivity, or fairly good sensitivity, and very wide frequency agility, so you can use it to do everything, but it will happily eat up and spit out lots of horrible stuff. So how is my radio lying to me? You can see the same signal showing up at different frequencies. For instance, I have no idea how this works. So you see, for instance, this might be the strongest signal in the band here, but it's modulating every other signal that you see. Every time this hits a peak, every other signal is hitting it. Or, it's not quite enough to say that. It could be a completely out-of-band thing that you're not seeing that's over here or over here. This is the AM radio spectrum here. And clearly something, probably this guy, but I don't know for sure, is modulating every other signal in the band. And that's caused by just so much signal coming in, it's overloading the front end of this relatively fragile SDR. You can also see you can see all sorts of other effects. You can see IQ imbalance in complex sampling SDRs. In CNLore's talk this morning, he gave a brief description of complex sampling. It's basically using two ADCs in quadrature to generate your signal. If those two ADCs are not balanced with each other, you see all sorts of imaging artifacts as a result of that. You can see signals appear on either side of the signal that you're actually looking for. Aliasing happens when you have poor filtering on the front end of your radio, RTL-SDR, where signals will appear at frequencies that they don't actually exist on because your radio is undersampling and creating these images internally. So in CNLore's talk, it was an advantage because you can use a radio deliberately to receive on frequencies it's not designed to receive on. But if you're actually trying to look in a place, if you have a poor front end, it may actually be aliasing other signals into that where you're trying to look for a real thing. And lastly, receiver overloading, which is what I just talked about, where so much CRUD is coming into your front end. You think you have an analog to digital converter. Well, eventually, you run out of bits. You run out of overhead, right? You've saturated that receiver. You can do it either in the analog domain, where the low noise amplifier, which is amplifying RF to feed into the ADC, gets overloaded, and it runs out of headroom, or you can overload in the digital domain, and they'll have different effects. So you can see aliasing in here. Justin, I think you can point out here what we're looking at.
Yeah, totally. So this was I was playing around with an RTL-SDR to do this talk, and I'll have a slide a little bit later that shows sort of unfiltered and filtered world with an RTL-SDR. This is the filtered view where you can actually see signals. But what's going on is kind of funny. So this is the upper HF spectrum again. So 26.9, I think it's 26.8 here to 28 something. But it's basically the very top end of what the RTL-SDR can receive on HF. And we see some signals. There's our CB again. God, they're so loud always. 5 watts too, it's amazing. But here's some ham stuff. So this right here that I have marked is actually my local neighbor's 10-meter beacon. I don't know, 6 or 7 miles from my house, but it's always there. You can always hear it. And I was looking at the lower HF spectrum when I put a filter in front of the AM broadcast that was there, and all of a sudden I saw stuff, and I was like, oh, that's a lot of stuff that shouldn't be in the AM broadcast band. What's that? So I started, put my sleuthing hat on, and I finally realized, simply by looking at this Morse code here and listening to it and decoding it, which you can do with an online, RTL web SDR device. This is my local 10-meter beacon, except it was over here on my spectrum, and this CB stuff was over here on my spectrum. What I've done is I've taken the lower part of the spectrum, the lower HF, so this is DC, this is 100 kilohertz, this goes up to 2 megahertz basically. I've taken this lower chunk of the spectrum and I've mirrored it left-right, and that's actually the upper half of my spectrum. And it's the same, right? Because we're aliasing that upper chunk of the HF spectrum down to what the radio thinks is DC, but it's not real, right? It's a totally different band. And that's after I put a filter in. And so these are the types of things that you really want to be aware of as something that can happen because it can be very confusing because the signal might be there. Then you pull out a different radio because maybe your RTL-SDR isn't as portable or whatever, different antenna, and it's gone. And you can spend a lot of time chasing your tail because it's there and then it's gone and then it's somewhere else and then it's there again. So these are concepts to really be aware of.
So your radio, so everything has a clock in it, right? Everything digital has a clock in it, and that, unfortunately, that includes your radio. So very often, analog or digital, actually, analog radios also have oscillators in them. They use as the local oscillator to mix your RF signal back down to baseband so you can hear it. So if everything has a clock in it, for instance, the RTL-SDR has a 28.8 megahertz reference oscillator in it, right? You're going to hear that. It's going to radiate too, because everything is a radiator. If there's one moral of this talk, it's that everything is a radiator, and anything with an oscillator will radiate. So especially cheaper radios, the RTL-SDR is one, a lot of other cheap hobby SDRs will do the same thing. You're just going to see signals that don't actually exist. It's the sampling clock for the ADC, or it's the oscillator for the processor that's on board, or it's literally, or it's a USB interface, or it's an Ethernet interface. It's any other electronic component that happens to be switching at any given rate. So that should be a clue. If it's always there, if it's unchanging, if you unplug your antenna and you still hear it, it's probably generated within your radio. A lot of times you'll also see these birdies are mixing products of some nonlinear process inside the radio. And so if you change frequency, if you go from 10 megahertz to 10.1 megahertz, you may see in your spectrogram, instead of that birdie staying at 10 megahertz, it may go down to 9.9. It may go to 10.2. It may change in a way either backwards from how you change your frequency. It may move around either backwards or at a multiple of how you're changing the frequency of the radio. And that just happens because, say it's a third harmonic, or say it's, the IQ imbalance, nonlinear mixed product of two signals inside your radio. It won't follow the frequency that you're tuning. So that's another good clue that it's built into your radio and you can't do anything about it. And sometimes these birdies, unfortunately, sit right where you want to listen to something, and there's generally not a lot you can do about it except get a different radio. So here we're seeing signal images. So this is an example of seeing signals that aren't there that are being mixed down. So Justin, unfortunately, the way the spectrogram is set up here, it keeps the frequency constant, but what he's actually doing is retuning the radio. So he's retuning the baseband frequency of the radio, the 0 point in frequency of the radio, and you can see if this were a real signal, it wouldn't move at all. It would stay because the whole spectrogram is being reset to keep frequencies constant. But you can see the image here of the repeater input is moving. It's changed. So this gives you a good clue that this image signal that you're seeing here is not actually being generated by anybody. It's just a birdie inside your radio. So receiver overloading, you're going to see every once in a while, you're going to see the noise floor of your entire spectrogram just jump. Okay, it's going to be wildly higher than you think it is. You don't hear what you should hear, and you hear what you shouldn't hear. You hear, as soon as your radio goes nonlinear, there's nothing you can do to get that information back. You're going to see all sorts of crap, all sorts of mixing products that don't actually exist, and a lot of times there's no way to actually recover the signal that you're looking for. So what do you do about that? Here's a good example of looking at what receiver overloading will do to you. Here's the unfiltered raw signal coming into the radio, and here's what happens after you put a filter out of band, by the way. This is the stuff that you're seeing. This is another lesson here. It may be way over here. It may be in the next room. It could be, again, if this RTL-SDR, if your radio has a totally wide front end, it could be anywhere from DC to daylight. It could be anywhere either within the passband that you're looking at here or somewhere completely different. So what do you do about that? You put a filter on it, and you'll see, you can see he unscrews the antenna to put the filter on here, and then puts the filter on, and all of a sudden it looks really great. What does that tell us? It tells us that the signal that's overloading the receiver is outside the passband somewhere, and completely driving the radio nonlinear, so you can't hear anything anymore. This is just a close-up view looking at the same thing in the unfiltered. You're seeing 10 kilohertz bursts here. This is a kind of a clue that it might be AM broadcast interference, which, another moral to the talk here, AM leaks into everything. AM is a curse, okay? They'll be broadcasting hundreds of kilowatts. It's at a very low frequency. It propagates everywhere. If you have mercury fillings, you can hear it in your fillings, so they say. But it gets into everything. I live in San Francisco, and I live like 3/4 miles from Sutro Tower. That's not AM broadcast, that's FM and TV broadcast, but same deal. I have 3/4 megawatt of RF coming into my lab every single day, and trying to keep my radios from doing that is an ongoing struggle. So what do you do about overloading? The first thing you do is you attenuate. The second thing you do is you can adjust your radio's gain optimally to try to minimize the effect of overloading. You can think if you have an extremely loud signal coming into your radio and your signal is much quieter, if you bring everything down, as long as you still have signal to noise in this signal left over, you win. Okay, because now as soon as your radio stops overloading, it's going to start behaving linearly. You're going to be able to pick signals out, and all of the horrible crud will go away. So a lot of times people will leave the automatic gain control on their radio turned on because it's simple. You plug it in, you turn it on, you get signal coming in. Why isn't it working? It's probably not working because the automatic gain control is cranked and it's overloading your spectrum even if you don't intend it to. So how do you optimally set the gain on your receiver? The best thing to do is to look at the noise floor and bring the gain down until the noise floor goes away, and then bring it back up so you can see noise in the spectrogram. You don't need any more gain than that. Once you've amplified the noise floor above the bottom, so that you can see it, there's nothing to be gained by adding more gain to your receiver. So that's if you're using an analog radio and you have RF gain control on the analog radio, the way to do it is to turn it down until you can't hear anything. Turn your AF up, your radio audio gain up. Turn down the RF gain until you can't hear anything, then turn it up just a little bit. Once you're there, that's where it's set. That's where you have the maximum dynamic range while still having optimal sensitivity for your setup. So now it's real. How do you find it? So Justin's going to talk about some clues that you can use to figure out how you can find it and what to do about it.
Cool, yeah. So one other thing I'll add to this last slide is this is very frequency dependent. So depending on your radio, depending on your antenna, it might be that a certain frequency needs more gain to bring the noise floor up at that frequency than a different frequency does. And we see this in the HF band. We've shown a lot of HF slot plots, but you can see it all over the place. The gain of your antenna, the gain of your radio, they change with frequency. Sometimes in order to get that noise floor to jump up where you want to listen, you've got to filter out something else to prevent overloading, right? So that's something to keep in mind too. A lot of these radios in general, you need a lot more gain the higher in frequency you go. That's sort of the rule with them. So once we've ID'd it, how do we find it, right? There's a lot of tricks of the trade to this. We'll share some of them. The really first question when you hear something is, where is it, right? Once you've determined it's real, it's probably being used for communication, or it's not real, or it's real, but it's not being used for communication. It's an unintentional radiator that I want to try to get rid of because it's, preventing me from using that frequency. What do we do? So we need to find it, and there's sort of three ranges here, right? Is it in my house? Is it in my neighborhood or city? Is it in my, is it worldwide? We talked earlier about those welders that show up in certain parts of the world. They're actually really loud and interfering, but there's nothing you're going to do about them because they're thousands of miles away. So we've talked a little bit about gathering this information, and so what do we have, right? Is it a continuous signal? Is it broadband hash? Is it a lot of spurs like we saw in some of those plots, or is it just one? Those are all questions we can ask to try to lead us to what's the source of this, how do we find it, right? We talked about patterns of life. Look at the time of day, right? If it's only happening in the evening time, it's probably residential, right? If it's only happening during the day, 9 to 5-ish, it's probably a commercial source. If it's only happening at night, it's absolutely vampires. Let's just be clear about that. And then, duty cycle, is it there all the time? Is it only there when I flip the light switch in my basement on? Is it coming and going quickly? All things to look for, right, to try to determine what that is. And we got to start thinking okay, if I was this source, how would I be behaving in order to create this pattern? And that's sort of what we want to look at. Is it drifting in frequency or staying constant? I think we had a plot earlier that showed a signal zooming through the band, and that's called an ionosonde or a RF sounder. So they zip through the band. If you're sitting still on a frequency, they'll sort of zoop by, and that's all you'll hear. But if you look at the whole spectrogram, you can sort of see the linear increase with time and frequency, increase or decrease. So if it is a noise source, and that's what we're looking for, it's probably relatively local, right? If it's broadband and it's noise, it's probably relatively local. So the first question is, am I creating this in my own house? So turn off everything you can, right? I like to put myself on a battery-powered computer SDR or just a handheld AM radio even, especially if it's a broadband source, and just turn the main breaker off. Oop, my house is off. Did it go away, right? A lot of times the answer is yes, because Nick will talk about this in a minute, but if it's local, if it's a noise source that's local, it'll be a lot louder than if you were farther away from it. So that's a good thing to look at. Noise, in general, has lower power than signal, right? It's being generated unintentionally. It's probably not connected to a good antenna, so it generally has lower power. And then so that tells you that this idea of 1 over r squared in how radio signals propagate is a useful tool to help you find that. You want to talk more about that, Nick?
Sure. Yeah, so when you're up close, the inverse square law is your best friend here. So as you have the distance, because spheres and radii, as you have the distance to your source, it's going to go up by the signal power you receive is going to go up by a factor of 4. So as you get closer and closer, that's super helpful. If you're 100 feet away from it and you go to 50 feet, you should see 6 dB come up. If you it's not super useful when you're further away than that. You know, if you're going to go take a walk, if the signal is 10 miles away from you, you're not going to see much variation. You're going to see more variation from multipath and from local conditions than you are in the signal itself. So when you're really close to it, when you're right next to it, that's going to be the way that you finally home in on what you're hearing up until the point where it gets so loud that it overloads your receiver, which is something you have to worry about. So you have to keep that in mind when you're getting very, very close, or you think you're getting very, very close to your destination. It's eventually the power will can come up to the point where it overloads your receiver. So what are we looking for? What are the usual suspects? What's the first thing that I should be looking for when I'm finding noise in my house? And number one is that cheap knockoff Amazon power supply that you bought for your laptop. Those things are almost universally noisy. They've got, if you look at the bottom of them, they've got an FCC ID or an FCC like logo on the bottom. That's forged. That's not real. We'll talk about this later, but the FCC is a complaints-based organization. They don't actually do proactive enforcement for the most part, and so until people start griping about this stuff, it will just continue to get sold. And unfortunately, it's kind of endemic now, especially at HF, especially with the shortwave bands. This stuff is so prevalent that the noise floor of residential, commercial, and industrial settings has risen like, I don't know, 30 dB from 50 years ago when our grandparents were doing ham radio. We had nice quiet bands. We don't have those anymore for the most part. So you have to be looking out for cheap power supplies. LED lights are terrible a lot of times because a lot of times they'll be dimmed remotely, where you'll be switching them. You switch LEDs by PWM for the most part for cheap LEDs, and when you switch that LED strip on and off, the current going up and down the wires supplying it changes very drastically, very quickly. Well, that's a transmitter, and so you'll see PWM noise from LED lights all the time. Fluorescent light ballasts are really bad if you have fluorescent lights. There's two classifications for fluorescent light ballast. There's A and B. One is residential, one's commercial, and I don't remember which one is which, but if you buy one requires more filtering than the other, and if you buy a fluorescent light ballast off of Amazon, guaranteed it's rated for industrial settings. It requires less filtering. It's not supposed to be sold to you and installed in your house, but it is anyway. It will make more noise. Cheap TVs are pretty bad, especially the older ones that had CCFL backlights. Those were high voltage power supply backlights. Those tend to radiate a lot of noise. And basically anything that has an oscillator in it. And in our smart world now, everything has an oscillator in it. And so look for something smart. Look for anything that has an integrated processor. Look for anything with integrated logic. Those things all have a clock, and if they're built badly, they will radiate. You can also look for bad transformers or power line insulators, and we'll talk a lot more about what power supply noise, transformer and power line noise looks like.
Cool. So we're going to zoom through the next few slides because we're kind of running short on time. But local noise solutions, add ferrite. Like that's really it, right? Unplug the thing and throw it away is really first. Like if you got one of those cheap things, just get rid of that, burn it. E-waste that thing and be done with it. But otherwise, add ferrite. Ferrite is really effective, especially at lower frequencies, but even at VHF. I have some super noisy PoE cameras in my house, and all the lines to them look like this, and it helps quite a lot. And if you can, choke it close to the source with your ferrite. Nick alluded to this already. I'm going to zoom through it. If it's somebody else's problem, like, oh, it's my neighbor, like, really you're hoping here that you have a relationship with your neighbor and you can talk to them and you can try to work it out. One of those earlier slides I showed with my neighbor's LED lights, we've kind of come to an understanding that at some point here soon I'm going to buy him a new set of LED lights, and that's fine because it'll take care of the problem for me. FCC is reactive, and they don't really enforce these unintentional radiators. The FCC is not going to come after your neighbor, so you really need to work it out. And if you can't do that, then you're going to have to live with it. So what does power line noise look like? This is getting on to actual, bad insulators, bad transformers, whatever's going on. It looks really bad, and it's really messy. And I'm going to go here. Hopefully, if I can hit go, it'll play one of these. So this is going to hopefully not be too loud. Nope, that's not the right button. So that's what power line noise sounds like on an AM radio. That's a different recording of it. So those are both when I was on a de-expedition to Palau. We've had really bad power line noise. We had to get the power company involved. We hunted down the power line noise as best as we could. And we ultimately kind of found where it was, but it's a real challenge. Where we were in Palau, there's literally one road up the island, and the power lines run along that road. So we went for a walk, we went for a drive, but we were ultimately driving up and down the lines, and the lines are a conductor of noise, right? They're an antenna, they're a transmission line. They'll take the noise with them wherever they go. It'll tend to get louder at discontinuities, transformers, splits in the line. But it's hard to figure out exactly where it is if you can just drive up and down this. But still go for the loudest spot, and a lot of times you'll find it. AM radio, use a handheld if you can that's on a battery. Start at the low frequency, turn the frequency up until you can barely hear the signal, move some more, right? Got louder that way, great. It's probably that way. Keep turning the frequency up and moving closer, and turn the frequency up and moving closer, and turn the frequency up and move closer. Iterate that until you're really, you get to the point where it either starts falling off again, or you get all the way to VHF. By the time you get to VHF, you're really close. You've clearly got line of sight of it. It's probably within, less than 100 meters. So it's right there. And then once you do get that close, there's some specialized tools that you can use. There's ultrasonic microphones. This is Nick and I working for a client overseas trying to find a power line problem that we ultimately were able to find. So this is an ultrasonic receiver. This is just me with a handheld and an attenuator plugged into a Yagi. And we hunted it down to a pole. We figured out where the pole was. You sent a letter to the power company and said, hey, you got a bad insulator on this pole, and we're still waiting. In the US, it's a lot better. They want to get rid of that leaking current. The power line, the power company does. So it's a little more helpful. All right, we're going to spend the last few minutes here talking about some actual location.
Yeah, so what if you have a signal that's real? You've determined that it's not noise, and it's not or maybe it is noise, but it's not generated within your radio. What if you want to find it? How do we go about finding it? How do we go about finding a real intentional transmission? There's a number of different techniques that we can use. I'm not going to go over these in any detail at all, both for time and because they're hard. Number one is triangulation. This is the easiest thing in the world. You just get an antenna and you point it somewhere and wave it around, and where it's strongest, you go in that direction. You can take hints from search and rescue. Use a spiraling path. Don't go straight there to get more information about where the signal is actually coming from. The other point I'd like to note is that oftentimes it's easier to use the null of an antenna than to use the beam of an antenna. So instead of getting a very directional antenna, use a loop antenna, which is very good at, it has a very omnidirectional pattern, except when you're looking through the loop where it has a very sharp null. So point that null towards where you think it is. When it goes away, it's in that direction. So write that direction down, go somewhere else, do it again, write it down on a map, and figure out a location for your transmitter. Long distance sources, over-the-horizon radar, number stations, interesting HF targets like that are propagating. How do we find those? This is an image of Chinese over-the-horizon radar, which is an absolute problem for radio amateurs around the world. They're broadcasting over the Sea of China with 10 megawatts of power, we think, maybe more. And we can see this pretty much year-round, 24 hours a day, everywhere in the world. This is a number station, right? Yeah. So you can hear clandestine radio transmissions usually from Russia. I think they're the only ones who are operating them right now. But we want to know where they are. That's cool. Where are they broadcasting from? That's neat information. This website has a list of number stations and information about them, including transmitter locations, which is super cool, and you should look at it. And schedules, yeah. So another way that we can look, more modern way that we can look for where a transmission is multilateration. It's a GPS problem, but backwards. Instead of a bunch of satellites that know exactly where they are and what time it is, you have a bunch of synchronized stations on the ground, and they all know exactly what time it is, and you have an unknown transmitter. So if you do the math, it's actually exactly the same. The nice part is there's a lot of example code for GPS solvers out there that can be directly adapted to a multilateration solver. All you got to do is correlate all the signals that you receive so you know their time offset relative to each other, and then you get time differences between each station where they arrived, and you plot all those. They ended up looking like hyperbola on a map. You end up plotting all those, and where those intersect or almost intersect is your location. So there's lots of examples out there. The one I draw your attention to, if you've played with Kiwi SDR before, they have a built-in HF multilateration solver that you can play around with and actually use different free open source, I'm sorry, no, it is open source, yeah. Open source stations around the world to receive interesting signals and multilaterate them. It's generally not super useful for close ranges just because the speed of light is very fast, and a little bit of error in your multilateration means a huge error in your position. So, but for propagating HF signals, it's actually super useful. Doppler techniques, we're going to roll through that really quickly. Basically, when you're moving towards a station, its frequency is going up. When you're moving away from a station, the signal goes down in frequency. So you can either do this to a moving source like a satellite, and you can try to correlate, as the pass comes over your head, the frequency going up and down, and try to draw a path from that. Or you can move yourself. And moving yourself doesn't actually be physically moving yourself. You can move the antenna. And more than that, you can either move the antenna back and forth physically, or you can do it electrically. You get 4 antennas in a grid like is drawn here, and you switch between them very quickly. It's called pseudo-Doppler. And it will shift your signal in time as you switch between those antennas depending on what direction it's in. So it's a very useful tool for triangulation. And often, sounds kind of dumb at first, but one of the most useful things is, in the US at least, you have to have a license for an intentional transmitter generally. So a lot of times you can go, for a lot of interesting transmissions, you can just go on the FCC ULS, their website, and you can search by geography, by frequency, by call sign if you know it. And a lot of times you'll come up with not only the transmitter location, but the transmitter hardware, how much power, the times it's operating, all sorts of good stuff. So with that, we'll go to questions. If you have any questions, go ahead.
For the internal noise coming from a radio, I know that on cameras, they'll map the linearity of some of the CCD.
Mm-hmm.
Use DSP to compensate for it. Has anybody done anything like on the SDRs to try and map the internal noise and eliminate it?
That's a great question. It's sometimes. Sorry, I'll repeat the question for you. Good. He pointed out that that in a camera sensor, a lot of times they'll take what's called a dark noise shot, where they'll image the image with nothing coming into the camera, and then use that as a power offset for getting a better dark field image and getting rid of interference or bad pixels in the camera. In a radio, that can be harder because there's, in addition to the power coming in, you also have the phase of the signal coming in, and it may or may not be correlated with the master oscillator of the radio itself. And so you'd have to kind of lock on to each one of those individual interferers over time and try to, it's almost like the lock-in amplifier talk from earlier today. You'd have to lock on to each of these interferers to try to null them out. So I'm not aware of any SDRs using that technique. I don't know if you are.
Yeah, there's some really basic techniques in some of the SDR software to just sort of remove the amplitude of what's there, but I haven't found them to be super useful for all those reasons.
I will say that there are a couple of things that you can calibrate out. One is IQ imbalance. There's a lot of radios that will self-calibrate their IQ imbalance to try to get both ADCs on the same page, so to speak, and get rid of images caused by imbalance issues. Any other questions?
So, who contracted? I know it sounds like a strange question, but how did that happen? How did you get a contract? I don't want to do it myself, but it just doesn't make sense. Who reaches out about this?
Okay, so the question is, who cares about radio interference and who's willing to pay other people to mitigate it? And there's a general and a specific answer to that. The general answer is anybody who has a communication system. This happens, I've heard about ground hunts for satellite interference, where somebody's got a transmitter on the ground that's actually interfering with coverage or uplink to a satellite in space. And they care a lot about that. Another story is the CIA. I don't know if you ever looked this up. There's a great Wired article about it. In the 90s, 80s and 90s, had trouble with Brazilian truckers, believe it or not, because they had figured out how to put a frequency multiplier on their radios and transmit on the Milstar satellite uplink frequency. And they just knew that when they transmitted on their radios, with it configured in this way, they could hear the other guy 3 valleys over, and they didn't really know why at first. It's because they were using military communication satellites. Obviously, the CIA cares a lot about that and invested a lot of resources into mitigating it. Specifically, I'm involved with a company that's installing shortwave arrays in various countries, and we were having what ultimately ended up being transformer noise on one of our sites, and I nerd sniped Justin into coming down with me to South America to hunt it down. So. Go ahead.
I know we all love neopixels.
Mm-hmm.
Can you comment on the joy of neopixels and what they do?
I don't actually know. Have you played? I know neopixels. I was unaware that they're horrible. The question is, do we know anything about neopixel noise? And I haven't personally experienced.
They're long strings of lights.
Oh yeah.
Light ones.
Yep.
With sending a signal, which is
Yep. So a nice long string of LED lights creates a very nice long antenna by which to broadcast any noise coming in.
so one for seasonality as well as
Yeah, that's a good point. Seasonality. I actually, this is a problem at my house. I chase down these things all the time, and Christmas time, from now until January 15th is like, I can hardly use the radio at my house. It gets really bad. So, cool. I think we're out of time. Well, thanks everybody for coming. We appreciate it.